give this amino benz triazole, which under oxidation with lead tetraacetate, which oxidizes this nitrogen to a nitrene, an N lone pair without the hydrogens, then that loses 2 molecules of nitrogen if you heat it up to give benzene again. And those are all relatively mild methods. I've given some references there to those processes. So that's a relatively mild way of doing it, and much more commonly used now is this desilylation method I mentioned. Now I've taken these images from a file on the web which was obviously trying to popularize this method, but they said it avoids using highly reactive bases, which can be pyrophoric. It's not shock sensitive like some of the diazonium salt ones. It avoids using the oxidant lead tetraacetate that I mentioned in the amino benz triazole case, and it's controllable at room temperature. Fluoride is the basis, so that's tetrabutyl ammonium fluoride, and the reaction goes via the fluoride attacking the silicon here to create a negative charge which continues to eliminate the leaving group, as I said, triflate or an iodonium salt. And the precursors are relatively easily synthesized. So that and the loss of gaseous molecules are the two most common ways now, although some of the examples I show in synthesis still use the strong base method. So what about the reactivity? There is a very low-lying, lowest unoccupied molecular orbital in benzene, and that means that benzene shows high reactivity and also a good tendency to react with nucleophiles. But here I'm showing cycloadditions, so you could regard this as the low LUMO really means this is a reactive alkyne, so that benzene undergoes Diels-Alder reactions where the extra bond in the benzene behaves as the alkene, the dienophile, and so you bring in other dienes. Here's a fairly reactive one like furan, and there's the cycloadduct. And of course one of the driving forces is that you restore the normal aromaticity, the normal benzene properties that are in your benzene. If these will do 4+2 Diels-Alder reactions, then they should do the 4+2 in electron terms, or 3+2 in terms of atoms, the dipolar cycloadditions. So this is a precursor of a nitrone. Oh, there's a mistake. Oh, right, mistake here. I beg your pardon. This is badly drawn. So this should actually be the nitrone. So it should be N plus O minus. I apologize for that. I don't know why I didn't notice that before. So this should be the nitrone, N plus O minus. And that does a 1,3 dipolar cycloaddition. Again, one of the driving forces is the restoration of the normal aromaticity to give that cycloadduct. And whether this is going via a pericyclic process or a stepwise process, not sure, but you can do 2+2 cycloadditions without needing photochemistry to make benz cyclobutenes. So that's cycloadditions as one aspect of the reactivity. What about selectivity? What about if you have an unsymmetrical benzyne and you want to know which carbon will react in preference to which other one? So, unsymmetrical benzynes, any polar group at the 3 position, in other words next door to the benzyne, dramatically changes or dramatically influences the selectivity. So if I've got an EWG stands for electron withdrawing group, then you can imagine that is creating a small dipole in the benzyne, which is a little bit more electronegative nearer to the electron withdrawing group. So that will be one effect. The other thing we need to think about is donating groups, like lone pair donating groups, like alkoxy groups and so on, aren't donating in this context because they're donating into the pi system of the benzene, but not the benzyne orbitals, which are orthogonal to the pi system. So donor groups which are donating through lone pairs, effectively in the benzyne chemistry, react just through their inductive effect, which in the case of oxygen will be in the opposite direction to the delocalizing lone pair donation effect. So here's an example of that. If we take methoxybenzene and we try to do a Friedel-Crafts reaction, this is not the actual reagent, but if we try and use something that will generate the tertiary butyl cation, then the methoxy group acts as an activating donor group and generates the para substituent. If it's benzyne chemistry, the lone pair interacting with the benzene ring doesn't really have much effect on the benzyne, because that's in the plane of the ring rather than above and below it. It acts as an electron withdrawing group now because of the electronegative oxygen, and nucleophiles will attack at the remote position of the benzyne because of the dipole that the inductive withdrawal there creates in the benzyne extra bond, or between the 2 benzyne positions. So we have to think of these things slightly, we think of them in dipole terms, and we think of it slightly different to reactivity with the normal benzene pi electron system, because this is happening in the plane of the ring, and so it's essentially inductive effects only. So here, reverting to the cycloaddition story, here are some examples, and the unsymmetrical nature of the benzynes is what's affecting the regioselectivity of these cycloadditions. The earlier examples I showed were benzyne itself, so there was no regiochemical issue. So here's a paper, here's some results from 1992, where we're trying to make, heading towards this natural product. So we have, so they created a benzyne with an activating, an oxygen substituent here, which, as I say, in the benzyne context is a withdrawing group. There was a sugar ring on the other end, and a cycloaddition takes place with this methoxyfuran. The bridged intermediate you get opens up, but the key point here is you get a single, or 9-to-1, not quite a single, but a predominance of one regioisomer rather than a significant mixture. And then that was taken on, that's this part of the structure. Clear, it's going to be this part of the structure in the natural product. Here's a more recent one. where, what's going on here? Oh yeah. I guess this is, right, this is a cycloaddition in its result. Whether you regard it as a cycloaddition or whether you regard it as an enamine attacking, I think is, yes, probably the best way to look at the mechanism is an enamine attacking at this carbon. The overall result is a cycloaddition because then the benzyne is attacking at this carbonyl group. You could argue whether I've got this example on the right page of these notes or not. But ultimately we're ending up with a 4 atoms plus 2 overall a cycloaddition-like product. And the regiochemistry here in both cases has been defined by the oxygen substituent and its inductive withdrawal effect. Now this one was taken to this cycloadduct, which was then taken through to this natural product. So I've got a couple of other stepwise cycloadditions here. Again, same regiochemistry. It says 3 plus 2 and 2 plus 2. The 3 plus 2 one is at the bottom here. And if you see this oxygen substituent is going to be inductively withdrawing on the benzyne. That is why we draw the mechanism as the first step being oxygen. Again, this is another mistake. There's a plus missing on that nitrogen. I apologize, I don't know how these have got through. Must have been making these slides late at night. So there should be a plus on that nitrogen, and in this structure as well, actually. So that the oxygen, the nucleophilic oxygen of the nitrone, adding to the remote position of the benzyne, remote from the oxygen substituent. So again, driven by the electron withdrawal of that oxygen substituent, which, as I say, in the benzyne case is only acting in an inductive withdrawal fashion. And then that reaction finishes off by the by the excess charge, the negative charge you generate at the other end of the benzyne, ring closing. And if that was N+, then you should have another curly arrow there. The 2 plus 2 case, shown here, same thing happening. The most electron-rich position of this dimethoxy alkene is the top one, and that adds at the remote position of the benzyne, and then the other position closes back onto the other position of the benzyne closes back onto the by now electron deficient carbon in the middle of this compound here. That was then taken through to hydrolyze this acetal and make a ketone. So in both cases, a single regioisomer here and a 20-to-1 regioisomer ratio in the dipolar cycloaddition case. I say two-step, but overall dipolar cycloaddition.
What about the stereochemistry in the second product?
Sorry?
What about the stereochemistry? The second product is phenyl.
The stereochemistry there, you mean?
Yes.
I don't know. It will be a racemic molecule because there is no chiral directing group in the reaction. So you'd have, yeah. No, there's no control over it in that case, which is why I haven't specified it. So there's no chiral element anywhere in here, so there's nothing to give you absolute stereochemistry there, so it'll be a racemic mixture. So I'm sorry about the mistakes here, but just to say again, that should be N+ in both of these structures. So that ratio is regio, so it's RR, it's a regioisomer ratio, so it's nothing to do with the stereochemistry. Okay, so those are examples showing the regiochemistry control as well as other reactivity. If this has a low-lying LUMO, then that means that's a low-lying empty orbital, so that means nucleophiles can attack very readily. Almost any nucleophile. Again, any adjacent electron withdrawing group would dictate the selectivity. And if you want to, and people have done this, you can calculate the charge, the amount of that dipole that the withdrawing group is inducing, and you can calculate the LUMO coefficients, and they are found to match the selectivity trends, so you don't really need to do that. You can just imagine that small dipole and see what happens. So anyway, here is an application to the synthesis of this natural product, indolactam. So benzene is used to make the bond between nitrogen and the benzene ring in this indole derivative. So in other words, to go via this intermediate. And here is the benzene that was made. I haven't shown how it was made, but this is the benzene that you reach. And the bromine here is an electron withdrawing group. So that gives you selectivity for the attack at the position remote to the electron withdrawing group, and the attack is by this nitrogen, this dipeptide ester. So this nitrogen adds at that position, which is formally delta plus in dipole terms, and you get a 12-to-1 selectivity for attack at that position rather than the other end of the benzene.
If bromine is acting as an electron withdrawing group, then the position ortho to that carbon containing bromo should be more electron deficient.
No, let's go back. The withdrawing group is creating a dipole that leaves the more electron density at the adjacent position, and the remote position is a little bit more electrophilic. So that's all of these examples have shown in the benzene case that electron withdrawing groups, the nucleophile adds at the remote position. So this is the way we believe it to be, that it's it's polarizing the benzene towards the electron withdrawing group. So that any nucleophile will attack at the position furthest away. And all these examples have all shown that. So for example, same here, the oxygen attacks, that's your withdrawing group, it attacks at the position remote from the withdrawing group. So that's again what's happening here. So this bromine will induce delta minus, delta plus, and that remote position is where the nucleophile adds. I mean, I know what you're saying. You're saying the withdrawing group will withdraw electron density from there, but I'm saying that has a further polarizing effect on the alkyne. So 12-to-1 selectivity in that case. This is a much more recent example from 2011. That was attacked by nitrogen nucleophile, lone pair nitrogen. You can also have attack by enolates, by carbanions, carbon nucleophiles. And here's an early example back in 1972 where this precursor was constructed, and you need to close this position onto that position of the benzene ring. and that was done by using a very strong base, so that's potassium and then a triphenyl methyl anion. So triphenyl methane having lost a proton, so that's a C minus, a very strong base. That base will form the benzyne here by HCl elimination. It will also form the enolate at this position by deprotonating next to this carbonyl group. And that enolate then adds to the closest position of the benzyne. Now in that case, the regiochemistry is controlled really by the geometry. It would be very difficult to reach the other position anyway. And that closes this 7-membered ring to make cephalotaxinone, which was then taken through to this natural product alkaloid. In fact, that's a straightforward ketone reduction there. That was believed to be the first use of arynes, which is a sort of generalized term for benzynes. So where you've got this triple bond in any sort of aromatic ring. First use of arynes in natural product synthesis. And that's going back to the 1970s. But it has been brought up to date, and here is a synthesis from just a few years ago of these natural products. And here, where benzyne is used here, a strong base elimination here, using sodium amide in tertiary butanol, THF at room temperature, to produce this benzyne and this enolate. So there's a ketone here with hydrogens on the alpha position. So that enolate then attacks, closes the ring across here. The reaction is completed by protons from taken from the solvent. And then that's further modified in several steps to these natural products. But you can see that's put the ring system together. It looks slightly different when you react with beta-dicarbonyl compounds. Same principle. So here is diethyl malonate. Here would be a benzyne could be made there if you treat with a strong base. So this is sodium amide again, to create a benzyne here. And what you end up with is this nucleophile appears to have been broken up. Part of it ends up on where the bromine was, and part of it ends up on the next door carbon. So what's going on? The enolate, this is a sodium enolate because we've made it with sodium amide. The sodium enolate of diethyl malonate adds to the remote position of the benzyne again, with this methoxy group having polarized the benzyne by withdrawal. But it doesn't stop at that position. There's an opportunity then for the negative charge that's created on the benzyne to ring close back onto one of the ester groups. That will make this kind of 6,4 structure, but that doesn't stay there. Normally, if you were going to do a reaction of a nucleophile with an ester, the tetrahedral intermediate will then expel ethoxide and give you a ketone. But here, it has another way out. It can break the CC bond to relieve the ring strain, and that CC bond was one of the bonds in the middle of the diethyl malonate. So it's breaking that apart, and then actually then you're treating it with KOH, and one of the esters, from this reaction this would be an ester, but then it's hydrolyzed by base, and it's hydrolyzed more rapidly than the other ester. But the key thing to see here is how the nucleophile gets broken into two pieces by a retro-Dieckmann fragmentation. So not necessarily easy to recognize that as a benzyne plus nucleophile product when you first see it, but you can write what then becomes a reasonable mechanism here. Here's an example of that same type of process being used. So here's a beta keto ester rather than a ester like diethyl malonate. And here is the benzyme being generated by the desilylation and leaving group route. So cesium fluoride this time as the source of fluoride to attack the silicon, give negative charge on one carbon of the benzene ring, which then can eliminate the triflate leaving group. If you treat that with a beta keto ester, again you get the product which shows two parts of the beta keto ester on different positions. And you can work through it. It's the same kind of process as I showed on the previous slide. And that was used in a more complex example to make this alkaloid, amyorinesinine. Here's the particular benzyme precursor. You know exactly where the benzyme is going to be because it's produced by loss of the silyl group and the leaving group. Whereas in some of the other cases, you've just got a halide. Of course, you could form the benzyme eliminating either side of the halide. But here, this method, you know exactly where the benzyme reactivity is going to be. That's attacked by this carbon of a beta keto ester, and then after the kind of four-membered closure ring opening I showed on the previous slide, then this is what you end up with, which is the center part, or this new seven-membered ring is the center part of this alkaloid when you eventually get through the other transformations that are required. So I think that this use of beta dicarbonyl compounds is quite interesting because it forms two CC bonds at adjacent positions as a result of forming initially one CC bond by attack of an enolate, a stabilized enolate at one end of a benzyne. And actually I think that's the last slide of this set. So what I've tried to show you there is why benzynes were first proposed, how they were, what was the evidence for them, what is the structure, and then what is the reactivity of the benzynes. Okay, so that's the end of this session. So we take a break now, and we at 11:30 or so we'll have the next session, which will be about something about radical chemistry. Okay, thank you. I should say for this reactive intermediate session, we will circulate the PDF files of the slides later on today, I guess.